Hello. Next, we'll do stability of completely filled and half-filled orbitals. So the first reason of the stability of half-filled and completely filled is symmetrical distribution of electrons. Symmetrical distribution of electrons. So we have two exceptions in electronic configurations up to atomic number 29. The one is chromium and the another one is copper. So when you have look in your books, you will find that the electronic configuration of chromium and electronic configuration of copper are slightly different from the rules discussed above in the previous class. So in case of chromium, the 3D orbital is half-filled instead of having 4 electrons. So the reason is symmetrical distribution. We'll discuss its electronic configuration later on. The second reason is exchange energy. Now, what is exchange energy? So it depends upon the number of orbitals to which the electron can exchange its position. The more the number of electron orbitals in which electron can go exchange its position, more it will be stable. So here is an example of 3D5. 3D5 means half-filled orbitals. Degenerate orbital are half-filled. All are half-filled. So first figure shows that 4 positions for first electron to exchange. Second, third, fourth, and fifth orbital. And in second, 3 positions for the second electron. And in case of third picture, the electron here in third orbital can exchange with these 2 orbitals its position. And in case of fourth picture, the 2 position. The fourth orbital electron can exchange its position with 1. This. So here 4 total exchanges. Here 3, here 2, and here 1. The total exchanges are 10. Right, like in case of CD4, the electron present here in first orbital, in case of 3D4, have only 3 positions to exchange, and in case of second orbital's electron, only 2, and in case of third, 1. So we are neglecting these 2 because we count them in the first picture. So the total exchanges are 6. So 3D5 is more stable than the 3D4. So now the exception configuration of chromium 24. The expected configuration shows 4s6, 4s2, and 3D5. This is expected as per Ohm's rule, as per Aqua principle, and as per Pauli's exclusion principle. Filling of orbitals from the lower energy level to up, then this rule is overcome here. 4s2 and 3d4 becomes 4s1 and 3d5. And the reason behind this is the symmetry, and the second is the exchange energy. So this atom becomes stabilized. The electrons become more stable in their orbitals by doing so. The one electron from 4s shifts to 3d5 and get stable as half-filled configuration. And in case of copper, the expected configuration shows 4s2 and 3d9, whereas the actual configuration has 4s1 and 3d10, and the same reason is fully filled configuration, and this is due to the symmetrical distribution and exchange energy. Next is the shapes of s orbital, p orbital, and d orbital. So brief description is here. So s orbital, L is equal to 0, ML is equal to 0. So only one orientation, only spherical shape is there. So in this case, uniform electron density all along the 3 axes. So this is the spherical shape which gives one orientation only. So so different S1s, 2s, have some differences in them. Like in case of 1s, there is no node. Node is an area where the probability of finding electron is 0, whereas in case of 2s, there is one node. And in case of 3s, the nodes become 2. And the number of nodes are equal to n minus 1. So in case of 2, n minus 1, 2 minus 1, 1 node. In case of 3s, so 3 minus 1, 2 nodes are there. Now, in case of P subshell, so P subshell L is equal to 1, and the value of ML is 3, minus 1, 0, and plus 1. So there are three orientations. So three orbitals of P which are degenerate have same energy, Px, Py, and Pz. Now, in case of P orbital, it consists two loops that are on the two sides of a plane passes through the nucleus, and the plane is known as nodal plane. And there is almost zero electron density on this nodal plane. So, and the p orbitals are known as dumbbell shaped. And this is a picture of a general p orbital. On the axis, there are two lobes, and electron finding density, electron finding probability is in these areas, and this is the nodal plane. And in this nodal plane, the electron density is almost zero. And these are the three Px, Py, and Pz, three different lobes, which are representing the three different orbitals of P. And one thing more important, these Px, Py, and Pz have nothing to do with minus 1, 0, and plus 1. This may be this is representing 0, this minus 1, this plus 1, or this is 0, this is plus 1, or so this is there is nothing there is no relation in between Px, Py, and Pz and 0, minus 1, plus 1. There is no relationship there. And the last topic is shapes of d orbital. So in case of d orbital, L is 2. So we have 5 orientations in total. So these 5 orientations represented as dxy, dyz, dzx, dx square, y square, and dz square. And these are the shapes. 3 orbitals are on the planes and in the planes, and the 2 are on the axis. 3 are in the planes and 2 are on the axis. And their shapes, the dz square is of donut shape. This one is of donut shape. And the other 4 are known as clover leaf shape. So this is all about the chapter 2. So I will send you some questions regarding this as an assignment. Now, thank you.